Good morning, everyone. My name is Soni Reddy. I am a research scholar at the Department of Engineering and Technological Studies under University of Kalyani. I am going to present my work entitled Single Feed Dual Band Circularly Polarized Modified Shape Square Dielectric Resonator Antenna for WiMAX and WLAN applications. My co-authors are Rahul, Mondal, Sushanta, Sarkar, Debasree, Chanda, Sarkar and Partha, Sarkar, all affiliated to the same department and university. This is the outline of my work. It starts with the requirements and challenges of designing antennas for wireless communication application. Then I'm going to discuss the proposed antenna design, its results, and finally end with the summary on the key achievements and future scope of the work. Let's begin with the requirements and challenges of designing antennas for wireless communication applications. Wireless communication majorly suffers from multipath fading and multipath interference. Therefore, in order to effectively handle the adverse effects of multipath fading and multipath interference, circularly polarized antennas are required. Secondly, any type of wireless communication requires antennas capable of providing high gain, high radiation efficiency and negligible power loss. Dielectric resonator antennas, which have dielectric block as its resonating element as shown in the picture given here, have been found as the best candidate satisfying this criteria compared to its metallic counterparts. Designing a circularly polarized dielectric resonator antenna covering multiple wireless communication bands using a single feed with a simple feed design is the current challenge in this domain. Now this is the detailed antenna geometry of the proposed work with its design specifications given here. The aim is to design a dual band circularly polarized DRA using a single feed and a simple design technique. We have used here a dielectric resonator block of modified square shape. The dimension is given as 24.4 cross 24.4 cross 12.2 mm. The material used here is Rogers 80,000 with relative permittivity of 10.2. We have used a metallic ground plane square shape and the dimension are 60 cross 60 cross 0.5 mm. The feed used here is a coaxial probe feed and the dimensions are 0.76 mm diameter and a height of 8.5 mm. The location of the feed is diagonally to the square DRA at dx equals to 8.5 mm and dy equals to 8 mm. The circular polarization technique employed here is DRA shape modification, keeping the feed unchanged. Now this is the design evolution of the proposed DRA. It begins with a conventional SDRA fed diagonally by a simple coaxial feed. Next, a pair of grooves is symmetrically placed along the YZ plane along the center of the SDRA. Next, we have a pair of ridges symmetrically loaded along the XZ plane. Finally, the pair of grooves and pair of ridges are offset by delta X and delta Y respectively, and this gives the final proposed design. Now, the rectangular groove dimensions are given here as 6 mm cross 14 mm. And the rectangular ridges dimension given here is 12 mm cross 4 mm. The offset location of the grooves is delta x equals to 2 mm from the center and the offset location of the ridges is delta y is equals to 12.4 mm from the center. Now this is the performance comparison of the analyzed design starting from design 0 to design 3. Now this is the S11 versus frequency plot for the analyzed designs. Here we can see that design 0 offers dual band characteristics centered at 3 GHz and 5 GHz respectively, but we have a narrow impedance bandwidth. Finally, due to the incorporation of the rectangular grooves and ridges, we find that from design 1 to design 3, an increase in the impedance bandwidth at the lower band is observed. Finally, the design 3, that is the proposed SDRA, is found to provide us the largest impedance bandwidth in the lower band, that is from 3.1 GHz to 4.2 GHz, approximately 1.1 GHz impedance bandwidth, and upper band from 4.9 GHz to 5.1 GHz, approximately 200 MHz impedance bandwidth. This is the axial ratio versus frequency plots of all the analyzed designs starting from design 0 to design 3 at both the lower and the upper frequency bands. Now we can see here that the final design, that is design 3, which is the proposed SDRA design, exhibits circular polarization in both the lower and the upper frequency bands with axial ratio below 3 dB from 3.3 GHz to 3.5 GHz in the lower frequency band and 4.9 GHz to 5.1 GHz in the upper frequency band, approximately 200 MHz axial ratio bandwidth in both the lower and the upper frequency band. Now this is the S11 and axle ratio versus frequency plot for the proposed design, that is design 3. The design 3 model has been simulated in both Ansoft HFSS and CST Microwave Studio Suite just to validate and compare the results. Now we can see here that the proposed design offers the circular polarization band at 3.3 gigahertz to 3.5 gigahertz, covering the wireless application WiMAX application band, and circular polarization from 4.9 gigahertz to 5.1 gigahertz, covering the WLAN application band. Now these are the modal field distribution inside the proposed modified shape SDRA. Now the orthogonal mode pairs generating circular polarization at 3.4 gigahertz is represented by the figure towards the left, and the orthogonal mode pair generating circular polarization at 5 gigahertz is given by the figure towards the right. Now this is the normalized radiation pattern of the proposed modified shape SDRA in both the lower frequency band and the higher frequency band, centered at 3.4 gigahertz and 5 gigahertz. These are the results obtained from HFSS. We can see that the proposed SDRA offers LHCP with minimum LHCP and RHCP isolation of about 23 dB at 3.4 gigahertz and 13 dB at 5 gigahertz in both the E plane and H plane. Now these are the normalized radiation patterns which are obtained from CST. Here also we can see that the proposed SDRA offers approximately 22 dB at 3.4 gigahertz LHCP RHCP isolation and about 25 dB at 5 gigahertz LHCP RHCP isolation in both the E plane and the H plane respectively. Now this is the peak gain and LHCP gain versus frequency plot for the modified shape SDRA which is obtained from HFSS. We can see that the proposed SDRA offers a peak gain of 6.3 dBi and 5.2 dBi in the lower and the upper frequency bands respectively. It is also found to offer peak LHCP gain of 5.3 dBi and 3.6 dBi in the lower and the upper circularly polarized bands respectively. It also operates with a minimum radiation efficiency of 98% and 95% in the lower and the upper frequency bands respectively. This is the performance comparison of the proposed design with the existing dual bands circularly polarized dielectric resonator antennas studied in literature. Now we can see based on this comparison table, we have found out the key achievements of the proposed design. First, it is found that the proposed design offers circular polarization characteristics using a simple coaxial feed, whereas the existing antenna design studied uses relatively complex modified feeding techniques along with DRA shape modification. Secondly, compared to the existing circularly polarized DRA designs, the proposed SDRA offers wider impedance bandwidth, that is 30.14% at 3.1 gigahertz to 4.2 gigahertz in the lower frequency band and 8.16% from 4.7 gigahertz to 5.1 gigahertz in the upper frequency band. And it also provides a comparatively wider axial ratio bandwidth of approximately 5.88% starting from 3.3 to 3.5 gigahertz and 4% starting from 4.9 gigahertz to 5.1 gigahertz. The proposed design also offers comparatively high peak gain of 6.3 dBi and 5.2 dBi in both the upper and the lower frequency bands. Finally, I would like to conclude the key aspects of my work and the future scopes of the work. Now, in this present work, we have studied the DRA shape modification technique for achieving dual band circularly polarized characteristics. The effect of loading a pair of rectangular grooves and ridges on the conventional square-shaped DRA faces has been studied, and it has been found that the proposed technique enhances the impedance bandwidth along with offering dual band circular polarization performance. The proposed design offers LHCP characteristics with a good LHCP to RHCP isolation and high gain in both the lower and the higher operating bands, which makes it highly suitable for WiMAX and WLAN applications. In future, we would like to enhance the CP performance of the antenna, which can further be optimized for better coverage of the WiMAX and WLAN bands. Thank you.